Okay, so to start with, I have to admit an embarrassing mistake I made in class. I just somehow wrote this wrong in my notes. So let me start with correction. I told you the wrong definition of a Noetherian, which is very bad. So a locally Noetherian scheme it's a scheme where every point has a neighborhood isomorphic to spec R with R Noetherian. And as we discussed before, this is genuinely different from being Noetherian as a topological space. So this is actually important. If I want to remove the locally, scheme, scheme such that every point has a neighborhood isomorphic to spec R. If to get rid of the locally, I should require that this is a finite cover. And there exists a finite cover of this form. So the kind of thing that would be locally Noetherian and not Noetherian would be an infinite disjoint union of Noetherian schemes. Schemes, or as ring spaces, right? We've talked about what ring, isomorphism. So, I mean, right, being a scheme means you're a ring space such that every point has a neighborhood isomorphic to an affine scheme, right? And this is saying I can choose that neighborhood to be Noetherian. And this is sort of a common type of definition. So if I have a property P of rings, usually we say that a scheme is locally P if the sort of analogous property holds. This is a neighborhood which is isomorphic to spec R, R having a P. And just P if there exists a finite cover with this form. All right. Yes. In fact, if and only if. So, right. Somehow, unfortunately, this is one of these things where there's kind of a complicated merry-go-round of how all these definitions relate to each other, and I will try to do them in a relatively coherent order, but it will definitely not be the only order in which you could say all this stuff. Yes.
So
and well, then it's P. It has a finite cover with one open set, which has that property. And I'll note here, quite often there is some variation in terminology where this would be some P prime, where just for whatever weird historical reasons, there's some slight variation on the name. All right, so, examples would be things like E equals Noetherian. P equals spec of a finitely generated K algebra. And this is for a fixed map of A into O of X. So if I fix a map of K into O of X into the global sections, the sections on the whole scheme, then that will make the sections on every open set into a K algebra, right? So my property P here is, maybe I should have, right? This is again one of these things where you sort of go back and forth, right? The property of the ring is being a finitely generated K algebra. The scheme terminology is locally of finite type, or well, I'll just say finite. Any old ring. Sorry if you're too used to K being a field in some other setting. Um, but yes, this, so for example, you could apply this with K equals Z. And that would just mean, every point in the scheme has a neighborhood where the that is spec of a finitely generated algebra, sort of period, in absolute sense. So finitely generated over Z. But of course, this is the sort of thing that comes up often because maybe you want to be a finitely generated C algebra, right? And then you're absolutely not finitely generated as a Z algebra, but that's only because C isn't finitely generated over Z, right? I should say finite type over K. And, I'll just mention here, this is sort of a hint that really a lot of these properties are what are called relative properties. They're really properties of maps. And so what I'm really fixing here, we haven't talked about what a morphism is, but I'm fixing a morphism of X to spec K. Even though we haven't defined morphisms of schemes, I don't think it will be shocking to you that a map from a scheme to an affine scheme is the same thing as a map of that ring into the global sections. All right. So another one would be a ring being radical. So then this is the ring word. The scheme word is reduced. Similarly, I apologize if you don't know this term. We'll talk about it in more detail later. Regular. So I mean that every local ring is regular. Such a scheme would also be called regular. Or integrally closed. Right, so these are all nice properties we look for in a ring. And that's integrally closed. Then the corresponding property here is normal. All right. One property we had mentioned that doesn't quite fit into this schema is integral. And we'll see in a moment why it's sort of not a good choice to put here. Integral has a similar kind of flavor. I would like to add integral here and, oh, whoops, the way around. Domain. I usually don't bother to say integral with domain, but of course, that was originally there in the terminology and we just got lazy. And for whatever reason, for the scheme property, we kept integral and not domain. Yeah. In its fraction field. Yes, that's true. Yeah, I'll say integrally closed in. I mean, actually, yeah, maybe this should actually go in the same bucket of, they're sort of, these are a little weirder. That's domain, yeah. I mean, domain is just people are too lazy to say integral domain. They mean the same thing. Okay. So how do we kind of more formalize this idea of taking a property of rings and then spreading it out across the scheme? Uh, as this question pointed out, it's gonna how that's gonna work is gonna depend on whether your scheme is quasi-compact or not. I'm interested in whether my scheme is quasi-compact. Note, quasi-compact, well, affine schemes are always quasi-compact. And so if you are a finite union of affine schemes, you are quasi-compact because a finite union of quasi-compact things is always quasi-compact. And in fact, the other way around, on the other hand, if you're quasi-compact, then any cover by affine schemes has a finite subcover. So quasi-compact is exactly the same as saying you're a finite union of affine schemes. Or you have a finite cover by affine schemes. We also talked about this property quasi-separated. So that means the intersection of quasi-compact things is quasi-compact. But a quasi-compact thing has a finite cover by affine schemes. So they're in the intersection of two quasi-compact things has a finite subcover by intersections of affine schemes. So this is actually equivalent to intersection of affine subschemes. That's certainly that these are certainly quasi-compact. I'm looking at the intersection. That has to have a finite cover by affine subschemes because it's quasi-compact. As finite affine. Okay, so somehow using the abstract topology words can be helpful for some purposes, but I think it's probably actually more useful to think of as a finite cover by affine schemes as the definition of quasi-compact, an intersection of affine subschemes has a finite affine cover is the definition of quasi-separated. Yes. Well, I always have a cover by affine subschemes. If I'm quasi-compact, that has a finite subcover. Yes, right? Because you just take an open cover and you restrict it. Right. Like if you have an open subset of a quasi-compact set, oh, let me be careful about this. Because wait, that's not true. Yeah, wait. Yeah, there's something a little wrong here because you're right that the finite subsets of Certainly there are compact sets that have open subsets that aren't compact. That part is for sure. Um, so the question, and what was I actually using here? Yeah, well, I don't, where would I have used that? I mean, it's definitely true that you can have, uh, right? Quasi-separated wouldn't be an interesting condition if it wasn't possible to have something quasi-compact and open subset that wasn't quasi-compact. But I don't think I assumed that anywhere. I pick an open cover by affine schemes, and by quasi-compactness, I have a finite subcover. I mean, I'm only talking about schemes here. Like, obviously, if I'm not a scheme, then I never have a cover by affine schemes, and that can't work, right? So being a quasi-compact scheme is equivalent to being a finite union of affine schemes. And being a quasi-separated scheme is equivalent to any time I have an affine subscheme, its intersection has a finite affine cover. Um, all right, so if I put these two together, then I get these two conditions together. I have a finite union of affine subschemes, and the intersections between those subschemes have finite affine covers. And as Vauquil notes, this is common enough that we call these two together QCQS. Somehow these four-letter acronyms are very popular in algebraic geometry. Yeah. Um, I mean, I think that's equivalent to it. I mean, on a scheme, you always have a basis of the topology, which is affine subschemes, right? You take a fixed affine cover, and then you take all the distinguished open sets in that affine cover, right? So what QCQS tells you is that um, you only need a finite, only need to start with a finite number of affine schemes to do that. All right. So a lot of the kind of tricky part of this kind of world of thinking about these properties of schemes, and in particular, how properties of rings kind of carry over to more general properties of schemes, is about kind of how open subsets can fit together, right? It's kind of hard to picture, right? Like things that aren't quasi-separated. I think I at least said the words of an example last time, but it's a very strange thing. So, I mean, somehow all reasonable schemes you will encounter will have this property, but you do sometimes have to think about, well, why does it have this property? All right, so one really important one is if I choose one open cover that has a property like Noetherian, what does that tell me about another open? Could I pick some other weird open cover where I get non-Noetherian rings? That would be upsetting. But sometimes things like that can happen. You can present things in one way and then you present it in some other way and it looks totally different. Um, Now, luckily for Noetherian, that doesn't happen. And the reason is what's called this affine communication lemma. So this says let P be a ring property such that, so one, if A has P, so does AF for all F. So all localizations that elements have this. And if I take F1 up through Fn, let me just double check whether I want to assume this is finite. Yeah, okay. No, that's fine. It's fine to assume it's finite. So I take generators of A as an ideal over itself, and AFI has P for all I, then A has P. Then if a scheme is locally P, E point neighborhood isomorphic to spec A is P, then all subschemes. Let's say all affine subschemes. So every time I find an open subset of X is isomorphic to an affine subscheme, or spec A, such that A has. All right. Yeah, sorry, scheme X, yes. So if I find one open cover with this property, that will prove that all affine schemes have this cover. Yes. Every distinguished open. Covered by distinguished. Yeah. And of course, if I have an infinite cover, I can take a finite subcover. Right? Because spec is always quasi-compact. If I have an infinite cover, then I can always take a finite subcover. Indeed. Let me even write that. So geometrically, if X is affine, then X has P. If and only if there exists a distinguished cover, a distinguished opens with P. Okay, so Noetherian being finitely generated is a K algebra, being radical, being regular, these all descend well under these properties. These guys don't, but for kind of stupid reasons. And the kind of stupid reason is that you can take disjoint unions. So these sort of don't quite fit into this picture, but they're close. And with a little care, that'll be okay. All right, let me say a tiny bit about the proof of this. So somehow the proof of this is I'm basically assuming, right, my condition on P is that this lemma is true if X is affine. So I have to sort of reduce to the case of an affine scheme. Yes, right, because I'm quasi-compact, right? So the point is, if you're quasi-compact, this locally property doesn't tell you anything, because you always, whenever you have a finite cover, you have a finite subcover. Yeah, which is why, like, right, you could imagine that instead of saying locally, we, said that this was the definition of P, and then having a finite subcover got some special adjective like finitely P or whatever, right? But because the vast majority of the schemes we ever work with are quasi-compact and quasi-separated, it sort of, isn't a very important distinction. And it just sort of, right, it's helpful that quasi-compact and quasi-separated is like already built into the definition of Noetherian. Okay, cool. So right, what's kind of the key here? So I have X, and I imagine that I have some copy of spec A inside it. And I know that I have some finite subcover by some spec BIs, but I have no idea what it has to do with A. Well, I know that I can cover spec of A by intersecting it with spec of BI for all I. So spec of A is equal to the union of, let me call this VI, where VI is intersection of spec A. Spec BI. Okay, but I have no reason to think that these VIs are affine. There's some open subsets of spec A, but I don't know what they are. All right. The key thing that I need to do is, well, it's tempting to say, this is an affine scheme. I know how to work with open covers of affine schemes. I want to take VI and replace it with localizations of A. And indeed, that is what I want to do, but I don't want to do that right away, because you immediately see the problem with that, which is then I do that and I have no idea what the connection to BI is. But I don't know, maybe it's not that bad, right? So every VI I can write as the union of VI intersect and let me be more careful about this. This is one of these things where you have to treat A and B slightly asymmetrically. And I want to look at my notes and make sure I do this the right way. Okay. Right. So when I think about VI as a subscheme of spec BI, well, I can cover it with distinguished open affines, right? Um, And then I could say, wait a second, wait a second, wait a second. There's nothing special about my BIs. I can replace the BIs with a covering of spec of BI by distinguished open subsets, right? So let's write this out in words. BI as a covering by spec of BI localized at Fj, right? Because that's a basis of the topology of spec of BI. Well, actually, I could just use these guys as an open. So this gives open cover spec of A by things which are of the form spec of BI localized at Fj. Uh, sorry. Well, it's yes. Okay. I mean, I don't know what it would differently mean if I had written, if I was saying localize, like if I said localize the spec at Fj, that would be a colloquial way of saying take spec, take the subset where Fj doesn't vanish, right? Which is equivalent to localizing it. So yes, I'm counting on you to mentally put in the brackets. Okay. Now I have to keep going. I don't know that these are distinguished open subsets of A. But I do know that they have a cover by distinguished open subsets of A. So inside here, for every, I have a cover of these guys, which is gotten by looking at spec of A localized at some elements D, J, K. Getting a lot of indices here, I know. And this is the union over K. So I have I and J fixed. This guy has a cover by distinguished open subsets. GI of A. Okay, I swear I'm almost there. I don't need to take another layer of subsets. Because I just note here, oh, well, this is an open subscheme of spec of A. So if I have an element of spec of A, I get a function on this guy. Restricted to BI, spec of BI, J. So my parade of kind of horrible notation continues. I can think of this as Hij in this localization. Right? So the key point here is if I have an open subscheme, then I can restrict sections to it. So if I take A and I localize that as Cijk, that's the same as if I take BI and I localize that Fj times Hij. And this is exactly the the thing we were discussing at the start of class, right? This subscheme is exactly the points where G, I, J, K are not zero, not contained in the prime. So when I take this guy, right, taking this open subset is exactly throwing out the prime ideals in here where this HIJK is in that prime ideal. So because the open subsets coincide, right? Because because the prime ideals in here that don't contain HIJK are the same as the ones in the whole ring that don't contain GIJK. I get that these open subsets coincide, and so I get an isomorphism between rings. Okay. So why is this important? Well, so that means that this guy has property P, and by one here, that means these spec AGIJKs have property P. And if I take the union over all I, J, and K, then spec of A is equal to the union of the distinguished subsets for all of these CIJKs. And these guys all have property P, as I already argued here. So by 2, that implies that this guy has property P. That's the same thing as localizing at their product. Right, but if I invert their product, that means I invert each one of them individually. Right? 1 over A is the same thing as B over BA. And 1 over B is the same thing as A over BA. Right? You can use the universal property of localizations, right? To say, oh, if I localize at A and then localize at B, I'm taking the initial ring, which has a homomorphism from A such that the image of A and the image of B are units. Well, the image of A times B is also a unit. All right. So let's talk a little more about these properties. So a property a property that some of these have and which some of them don't is what's called stalk locality. So on some level, a sort of simpler version of this story X has a property, and just to avoid a little bit of confusion, Q of local rings if and only if all stalks XP have. So this is a property that's called stalk local. And this is a property that's called affine local. All right, so these properties are all stalk local. Um, so in particular, you are radical if and only if, uh, sorry, you're as a scheme, you're reduced if and only if all your local rings are radical. All your local rings have no nilpotence. So here we say reduced, here we say radical, here we say regular. If the local ring is regular, and technically I shouldn't be saying regular because we haven't talked about dimension, but I assume many of you know about curl dimension. So uh, local ring is regular if the maximal ideal mod is square, has dimension over the residue field equal to the curl dimension of the ring. And then finally, we say the scheme is normal if and if the local rings are integrally closed. Yeah. Yes, um, because of the issue about taking disjoint unions. So, right, uh, being normal does not mean that you are integral. Being normal means that your local rings are integral domains and integrally closed. Um, oh yeah, yeah. I mean, this is also called a local ring. Yeah, yeah. What? The local ring? Well, again, this is one of these things where it's not quite grammatically a definition because sometimes we use a different word, right? So I'm trying to explain to you what a stalk local property is. So a stalk local property is a property on a scheme which is defined by some property of local rings on the stalks. Yes. Okay, this is we're having this issue about the two meanings of local rings. The stalks are ring. There are properties that rings which are local have or don't have. Some local rings are radical, some local rings are not radical. Some local rings are regular, some local rings are not regular, right? And depending on whether the local rings, the stalks of the structure sheaf of a scheme have those properties, we then have names for the schemes, which are sometimes the same and sometimes different. So if those local rings are all integrally closed domains, then we call the ring normal. Um, and integral domain, so you could define like locally integral to mean a disjoint union of integral schemes, and then that would be a stalk local property. Um, but integral includes in it being irreducible. So it's not, you can't sort of find it stalk locally. All right. Are there any questions? Yeah. Um, no, the issue is there are some stalk local properties that don't satisfy this condition. And they don't, for example, being an integral domain does not satisfy this condition, but kind of for dumb reasons, which is if I take two domains, R1 plus R2, right, then spec of this has an open cover where the open subsets are spec of domains, right? If I take, well, we saw this in the homework, this is isomorphic to the disjoint union of spec of R1 and spec of R2. So this is an explicit demonstration of being a domain does not satisfy this property. And so that's why integrality is not an affine local condition, but being a disjoint union of integral things is. Right? So you can prove that if something is locally integral, then its connected components are all integral. But it's just sort of, again, these terminology, they come for kind of historical reasons. And, somehow like being actually integral rather than being a union of integral things comes up more often. So people decided that was more important to have a name for, even though it doesn't quite fit as well into this schema. Yeah. Absolutely not. 1, 0 times 0, 1 equals 0, 0. Right? I mean, if, being a the spectrum of a ring is irreducible as a topological space if and only if that ring is a domain. And this is obviously not irreducible as a topological space. Right? And somehow geometrically, this is saying I have a function which is 1 on here and 0 on here, and a function that's 1 on here and 0 on here. And if they take their product, I get 0. Right? But that's somehow something you can't see by taking the local rings. Right? If I took the local ring of every point in this union, I would get a domain. Right? So somehow this is exactly sort of why you have to be a little bit careful about stock locality for this stuff. All right. Any other questions? With which properties in the stock? Um, well, property is a very general term, right? Um, so I hesitate to say that this is a common kind of issue that like stock, right? Stocks can't see global properties, and sometimes things just don't glue together correctly, right? Um, but right, given that we've been talking about quasi-compactness, right? Quasi-compactness is not something you can see looking locally around a point, right? Every point has a quasi-compact neighborhood. So it's exactly kind of a global property, right? And similarly, quasi-separatedness, maybe you can actually see more locally around a point. But, sort of somehow I think there's a more general point here that there are some properties which go from local to global well, and some properties that don't. And going from local to global could mean two different things, right? This is sort of the local thing is being spec of an affine. Here, the local ring is being the local property means the actual local ring. And there are a few things which kind of don't quite fit together correctly there, like this finite type thing, right? Being finitely generated as an algebra isn't something you can see from the local rings, because the local rings aren't finitely generated, right? Um, so this is just something you have to be a little more careful about. All right, any questions? Well, I'm out of time, so I'll stop for today.